Okay, next up, we have Edmund Rogers from the University of Illinois. Give him a round of applause.
All right, so I do cybersecurity research at the University of Illinois with a bunch of different people on this project, from Illinois and Oregon State and Rutgers and PowerWorld. And here's some pictures of some of the key people on the project. Somehow I got involved with those guys. Now, Kate was supposed to be here with me. This would have been her first hacker convention talk. She's done many IEEE type speaking engagements before. She was really excited about being here. Her husband was much more excited when he crashed his bicycle and he needs his shoulder reconstructed or something. So Kate sends her regrets, and I'm going to be responsible for her part too, which is all the power stuff. So it's going to be pretty cool. But the research project that we were on, it was funded by ARPA-E. We're at the end of 3 years. And at the end, one of the goals that we had was we were going to ensure that our software was going to have impact. And in order to do that, I really pushed for open sourcing the engine that we use for cyber-physical impact analysis. Primarily, this was developed for use in the power grid. So the idea being, how can you ensure operational reliability and understand the impact of, the C word, or the network attack surface around a large system that provides power to many people. And you have more cybersecurity things than you have time to take care of it. How can you effectively prioritize those things so your effort can be directed where it would have the greatest impact on reliability of operation? Because the problem is very complicated when you think about, there's internet connectivity coming into the corporate network, and then we've got all these little field devices, and then you got nasty hackers trying to go into substations, or we're going to come in through the internet and attack the land. So it's a very large, complex problem when you look at how do you put everything together so that we can look at adding on to traditional contingency analysis. Because planners in electric operations manually define contingencies like, we're going to lose this substation, or we're going to lose this generator. And they're like ecosystems or big things within the power grid. But we want to try and then they automatically insert these things, and they simulate the impact of what would happen if you lost that substation or that generator or something big. But it was always meant to be this like N-1 criteria where we lose one substation, what's going to happen? And then traditional contingency analysis has always been that way, where we're gonna plan everything based around that one thing. But what happens when you add this cyber on top, where maybe it would be you could simultaneously bring down or provide a denial of service condition to multiple locations, and how would you plan for that? Short of, we can make a big giant blackout, but then there's like a middle ground between that. Like if I get 5 things happen at once, what is the contingency for that? And previously we couldn't do any computation with that, but newer, more modern hardware has given us the capability of providing for much more fine-grained information about impact. And that's what the research project was all about. And because of the advent of more modern communications in things like the power grid, you have this idea about the size of the contingency list can just grow very large. If you look at 1,000 lines, and doing an N-1 means you have 1,000 different criteria. But you go down to N-2 and just take 2 things out, then you're just getting really big. And so what do you do? Because when you look at game theory, and there's a lot of game theory people on our research project, they wanted to compute everything, and it got really, really large fast. And we're like, what we want to do is come up with a way to reduce the where we're going to be calculating. And we do that, and I'm going to get to it in a little bit about, which is my part, about we add network attack surface to reduce the space of computation so that we can come up with a ranked list of contingencies. So if you look at like things like this is the beginning of the 2003 blackout. What the tool can do is take all of the different physical components that are inside of a substation, and then we map them, map the cyber and the network attack surface around it, and we can provide a mapping. So this is like normal, and so when something happens, there's a little bit of a disturbance, and then depending on what the piece of equipment is, how long it takes to clear the fault determines whether or not the thing would cascade beyond the bound of whatever it might be. And then if something bad happens, we all know that this was probably bad. So modern computing has allowed us, instead of just looking, oh, we lose this substation, something bad happens, you can actually go into an industrial facility after doing some of this inventory work. And I always like I want to go into a substation and point at something and go, I want to know, does this thing have an IP address? How is it connected on a network? What would be the impact if this thing were to be misused? And so the project tries to answer that question. And this is kind of like a preview of what you're getting ready to see. This is what the front end looks like and what you're able to download now. It was released 4 hours ago. But CyPSA streamlines the utility's ability to inventory and analyze cyber-physical assets. So it brings out, first we have to do work to collect the data from the individual devices that make the power grid, and then provide a mapping between the physical device and then its manifestation in the planning model, and its, if it exists, its IP addresses and network attack surface. And as we did the research, we came up with use cases. And like the first one I kind of touched on a little bit was asset ranking. So the idea is like, I've got a fairly large or a medium size, or whatever you want to call it. I have a bunch of substations. I have 10,000, 100,000 assets. Do you know which ones are the top 50 individual computing devices that are in your network? Likely not, because planning has always been, I always viewed it as being from the top down. So we're going to look at this substation, and we like to think we do cyber physical from the bottom up. So we look at all the individual components in the power grid and then rank those assets. And they can actually be ranked in within like the threshold for voltage stability, which is like 15 minutes, because a utility will calculate how they're doing every 15 minutes typically. So the control panel kind of looks like this. I'll do a demo later. I'm not going to hold on this too long unless the demo screws up, but you can get a linked list of what your top assets are, and then we calculate a cyber cost based on network availability and vulnerability scores from the ICS CERT database. So we can ingest and map data to come up with this score. And then there's also a performance index, which is related to what's the impact of the equipment on the power side. And then some of the other use cases that came along as we were doing this at utilities, because we actually have deployed this software at certain utilities, is this idea about patching. So you need to patch a lot of things. And I want to know, if I only have a limited amount of time to patch things, which things would get the best benefit out of being patched first. So if you're able to provide a ranked list of all your assets, you know which of the assets you should patch first, and there's actually a little box in the tool that says, I just patched this asset, then the tool will recalculate the list of top assets based on the fact that you've patched certain assets, and you can also keep track of which ones are patched and not patched. So hopefully that'll work in the demo. If not, there's a screenshot, of course. So the idea is we have a network attack surface over here, and we can map the attacker. And I don't know if I can use the mouse for the people online, but on the left over here we have the attack path, and this is like a standard network attack surface kind of graph. But we also can graph that into a physical one-line diagram. So if the electrical engineer is here, she'd be able to tell you a lot more. But I know, even as a cybersecurity guy, 126% is bad. So the guy gets in on that device, that line goes to 126%. And in the animation that we actually can run, and I'm probably not going to do it today, it causes a little blackout. So the other thing that's really cool, if you think about it, is aggregate exposure. So how many, Willie's 385s do I have in all my stuff? Because if there's a vulnerability and a certain revision level or model has a vulnerability, what happens if they all go out at the same time? We can actually model that now. So there is a way to just select or show how many of each different thing you have and what the impact would be if those things were to go down. And then this then leads into another case we got from actually utility feedback, is they wanted to be able to do cyber incident planning, where they wanted to be able to come up with more realistic cases of a cyber incident, and then what could they do to plan to make for a more reliable system. So the idea would be in the blackout, there were this is the actual 2003 blackout in a power flow diagram. And then if you had a way to map all the individual components, you could show where the most important things were and then the impact of that event, like we showed before. And this piece probably would have been a lot better if Kate was here. But this is the transient stability problem, where within 5 milliseconds, if the fault doesn't clear, there's a problem. So we want to take all the individual components and determine which ones have this 5 millisecond threshold exceeded, which would mean that it would impact devices around it, and that could perhaps get larger. And again, of course, this is what you're going to get in a download, and we'll see if the demo actually works later. But so the aggregate exposure, like I said before, so if I wanted to come in and there were 3 different things in common, so I can have multiple pathways coming in, and we can then simulate that and know. Now, again, not even being an electrical engineer, 114 and 142% bad. So, and then this is just a power world flow diagram. And
the blue line on the left side or the blue dotted line?
An attacker.
Okay.
It's a threat model, it's an attacker. I don't like the word attack, but the academics I work with love the word attack. So I really try to remove the word attack as much as possible.
How would you call it instead?
What would I call it instead? A day that ends in Y. So the question was, how would I call instead of the word attack, what would I use? I would say it's just a day that ends in Y. So things happen, and if there's if you have something in common amongst things, there's not really until now there wasn't really a way to effectively model this. And so one of the things that we've been really working on is, how do you visualize these things? Because there's a lot of junk in this, and it's a very hard problem just in visualization. So actually the first thing is, if you go to this IP address, this is actually live right now, you can see what we did was we took the IEEE 8-bus model and then modeled all of the protective relays and everything, the distance relays, and you can see a cyber physical representation of the IEEE 8-bus model. It's actually online. This is using Gabe Weaver's CPTL. And then I did a talk with him about this a couple of years ago. CPTL is cyber physical topology language, and it's in the plumbing of the engine So it provides us with ontology so that we can describe the relationship both from a cyber perspective and a physical perspective of individual devices that make up this system. And that kind of like all works together with you can use your network software of your choice because there's a JSON format, and I'll get into this in a little while, and then we have planning software, and the engine is what's been open source today. You can put your own impacts and network attack surface and make your own ranked lists. And with the whole idea, the goal of the project to be grid reliability. And I released it, I think it was 11 o'clock this morning, after we got the license attached to the software, which I noticed there was no license. I'm like on the phone, like, oh, wait a minute, maybe we should put a license on this. So it's open source under the NCSA UIUC license, and what we did was we worked to remove the dependency of any particular piece of commercial software. So I have a slide about that later. The idea is, and I think I've already kind of talked about this a little bit, the physical connections and the impact together are, so like I've got in the top here, the host may be compromised, or line K, then line K is at risk. And then this is all manifested back into what is the protection scheme at the substation, and then which individual device is at risk, and then what would the impact be if that device were compromised. And then with this critical clearing time, we can determine whether or not it's going to be an issue, because the planner will tell you, if it clears within 5 milliseconds, I don't care about it. So now, let's see what happens. And if I remember to turn the porn off on my, because I was waiting in the speaker room. So this is that IP address thing that I showed, and I will provide the slide so that you know what the IP address was, but it's 72 dot whatever that is. This is actually hopefully online. So this is actually out on the internet somewhere. So you can see that the visual representations of the 8-bus model, you can go online and look at those. By going to that IP address, you can get me afterwards. And then the other thing is the actual tool, which is right here. So when you download CyPSA, or Armadillo, which is what it's called, the release is called Armadillo, you're going to get HTML5 front end. You need Tornado and Python to run it on your machine. And I could go through and start it, but I actually went ahead and loaded it. I could show you later. We'll see how I'm doing on time. I think I'm talking really fast right now, so I don't want to attempt starting it right now because it's all running and it might screw itself up, because it does open up a port inside your computer because we connect to like 5555. So when I click on CyPSA analysis, so if you have multiple projects, you can select those, and there's a folder structure for that. And so I can go in there and select that, and then the little visualization will appear. And I can view the cyber assets, and then we can also view the physical assets. We get the one-line diagrams. And then if I start this, it kind of looks like this. So now here we have a ranked list of assets in the 8-bus model. So if I click on different IP addresses, I'll get the corresponding pass if it's still working. It was working because the paths were up there, or I can view the physical, that's still working, and then the cyber connectivity in that specific location. There's also a couple of other features in the tool that's been released today, and that's, let me go back here. There we go. So there's also the other visualization. So we use D3 for visualization, and that's coming up. But this is the this is going to look really, really small on this video. So this is the 8-bus model. But if I click on individual substations, I can then get we have a tree view on the left, and then we can show both the physical, the big from a planning perspective or one-line diagram perspective assets, and then, or click on individual things, and the network would come up, or the network elements, or the cyber elements, the network attack surface of individual substations. And then there's also, this is another tree view of the same CPTL-based things. Once we get the mapping of this relay is this IP address, it serves this function, we can tie all those things together via ontologies and then look at all of the different components that make up the different substations. So I can select any substation at random, or if you can see that, somebody can pick from the audience and I can show, oh, not if I do that. There we go. Let's see. So how about you pick one, and we'll see if it actually works still. Somebody. How about Haverbrook? Okay, there you go. So this is a Haverbrook substation, and then I can look at the different cyber and physical components that are in that substation. It looks better on if you have a bigger screen, obviously. And then, get back here. And then it kind of can get big, and here's where we hit the D3 wall. So we actually have a model that has 300 substations in it, and it's about 5,000 devices. So this is 5,000 devices, and D3 kind of like starts to shit on itself. So like if you wanted to zoom in, it takes like 30 seconds. So I could get all the way into here, but I don't have that much time. Even as fast as I'm talking right now, I don't have that much time. But so it's kind of there, but going back, and some of the other trees that we used in the visualization really help us put more information visually on the screen, because one of the things we learned in the research going into utilities is that it seemed like we were more interested in the visualization than the utility actually is, because all they really wanted was either a CSV file or a list. We want the list. We want to see a table. And that's really where they always go back to the home interface, where we just go into, this is not the right one. We go into here, and they want a nice table so they can see their top assets. Now this should be working. There we go. They want to see their list of assets, and I think if I come down here, and with the video, kind of like, you can maybe see that now. I can mark two things I can do with the engine that are kind of cool is that you can mark a host as being patched so that you know which ones haven't been patched yet. So a utility asked us for this, but the other thing I thought was really cool is I could actually mark a host as being compromised and then recalculate the rank path based on that. And then you can also go through and see the vulnerabilities based on CVE score for each of the individual components that have IP addresses. And we tie all that together, and then we can also mark the vulnerabilities as being patched, and then recalculate the pass. And then, did I forget anything? I'll find out when I go back to the slides. I think there was one more. And yes, there's one more. So this is actually D3. So this is the 8 substation model. And one of the things, it's like, okay, that looks like some kind of blended salad. So what are you going to do when you have all of these different devices? And one of the things that we're working on, and we built the trees, is that I could show you all the different devices, but then how does this make sense? You add names, do you not put names in? These are all traditional visualization problems, which is why we have a blend between, you want a visualization, you have a smaller network that's going to be fun, especially from an open source perspective, because maybe you don't have 5,000 devices. One of the things the B-Sides folks asked us to do is to come up with a way for, I'm not a power guy, how can I use this? So the visualizations are very mature and stable. We had professional programmers working on some of this, some of the visualizations, and then you can always go back to the tables because you can get a lot of from just tables because people understand either the name of the device or its IP address. Cyber guys are always going to look at, cybersecurity people look at the IP address and know what you're talking about. And then like operators always ask for the name or they look to see the name, and you can change these kind of things once you have everything into a database. So I'm going to go and see if I forgot anything here. I'll need to pick the right slides. Okay. So here's how you start the tool. So let me see. Not bad. So when you go to GitHub and download Armadillo, you're going to need to be running Tornado. It's some guy shaking his head, yeah. So then all you're going to do is, and it's not start Tornado, it's, I think it's not, it doesn't say that, it's something else now. So that's wrong. It says start CyPSA. It doesn't say start Tornado anymore. But then it comes up just like I showed you in the demo. You click on CyPSA analysis. Maybe I should have looked at these slides before I tried the demo because I probably would have done better. Click select. And then 8-bus analysis comes up. A bunch of stuff starts to go in the background. And this is the engine doing its thing. And then you can go in and look at your ranked list of contingencies. And then here's the list of assets. And then we have this, like I said, the security index is determined by the cyber cost and the performance index. And you want to contact any of us, we have contact information. There's been papers written on some of the formulas behind the performance index and the cyber cost. And there's more papers being published towards the end of the year regarding this research. And did that, showed you that. There's the tree view. Maybe it looks a little bit better in the slide, where you can select out on a different yard and it shows the connection between the distance relays. This is our attempt at really better organizing than we can get out of D3 because it's so jumbled when you put a few hundred devices on a small screen. But it's more than just power. The CyPSA engine and the web front end there can be used on things other than the power grid. And like I said before, there is performance index JSON template, so you can make your own performance index for individual devices and then build your own network attack surface via the JSON provided in the open source and use the engine in something that's called offline mode. And then you're like, well, how do I do that? Shit. So, well, this is like literally something that was done last week because I was very insistent about having a standalone product that would run without any proprietary information from commercial products. So Olivier calls it offline mode. So you actually have to type offline in the command line. He wrote these up. We had Olivier was we had him on loan from a Marine Institute in France. He's a Frenchman, and he calls it offline mode. So now it's offline mode right now. I don't know if it's going to stay that way, but it's actually in the command line. So you would do run CyPSA bat 8-bus boop, boop, offline. And you can also change the output in cpgen.csv so that you can pull your own information in. And Olivier is not in America anymore. He left last week. And but I thought that I would want him to be in the talk. So that's Olivier. He really indoctrinated himself into America while he was here. And he was amazed at the size of the soft drink. So CyPSA is available on GitHub as of 11 this morning. There is the papers involved with some of the formalization path analysis that we did at the Illinois website under ITI CyPSA. And then Cadego is a company that has been formed to work on servicing the open source, kind of like with Snort or something like that, where you want somebody to come in and do this. And part of the ARPA-E project was path to commercialization. They want to see the research have impact. So CADEGO can kind of help with that. And then Kate would have been happy to be here to talk to you about it. This is her company. My role at the university is to help researchers see their research have impact and to perhaps have them start companies. And this is the second one I've done at the University of Illinois. So I think that's it. And I have plenty of time for questions.
If people have questions, could you just come up with the microphone?
How's it going, Ed? Chris is drunk.
Hey, Chris.
Mandiant. So your model, I'm an electrical engineer. I don't know if you know.
Okay, so be gentle. I'm a hacker. I'm not an electrical engineer.
Right. So I used to work for Entergy, and so I actually know Matt Davis. That's Kate's husband. We went to school together.
Yeah, he's okay.
Yeah.
But he's not. He's very happy right now.
Yeah. So we went to school together at Tech. Well, anyway, my question is I know it focuses a lot on the relays and things like that. Does this project also include things like RTUs, substation RTUs?
As a matter of fact, it does that. But the idea is, we can map impact of anything inside the substation because with the ontologies that way, the sexy things are the relays and
Sure.
because they have the greatest precision. I need to understand what's going to happen 5 milliseconds, within 5 milliseconds after something
Right.
happens in a relay. RTU goes out, oh no, we don't have readings from this site, the grid's not going to go down. There's different performance index, but it can be included. But if you have 10,000 things, they're going to be towards the bottom of the list.
Yeah, we had to do risk ratings for every type of piece of equipment. For relays, I had to do them for RTUs.
Yeah.
And I wanted to include cyber at the time, but we didn't have very many RTUs on the network. So if you have an older substation with a lot of electromechanical relays, but you have a modern substation gateway or RTU with IP, that would be really good to
And
take
the other
it.
thing is the idea behind, we see this a lot out in the field too, because we've been to a lot of utilities, is that we can model serial or like non-routable protocols because it's just a relational map to us. A can get to B to get to C, and it's much easier to model than when we're looking at a larger utility that has maybe multiple pathways. And you can still map impact on that, but you lose so I won't have an Nmap, there's no IP address, so you have to adjust your cyber score because it's different. Because your cyber score is probably either 1 then, because if I can get access to that, I own it.
Right, exactly. All right, thanks.
Good question.
Ed, would you be so kind to share with us, if you could, the future I guess what's next? I mean, I see that a company has been founded. I know that at Illinois there's going to be a lot, you're expecting a lot more paper to get out, there a lot more publication. But, is this going to be used? I mean, is this going to be shopped around to utilities and power industrial companies? I mean, could you share a little bit more about how you're going to, what the approach is?
Sure, I can do that. So I didn't want this to be a vendor pitch. Yeah. So, we are out in WEC. We've been at WEC User World meeting. We're working closely with planners. We're with a big utility out in WEC. We've actually modeled the Northwest with this. And we can do transient stability studies and critical clearing times for some of WEC. I don't want to misspeak because I think this is live, but for some of WEC. But it's possible to do all of WEC. We just would need to model it. And so we're actively involved in that kind of thing on the CADEGO side of the fence. But this is not a CADEGO talk. This is a talk about the engine. We use this engine, and we want other people to use it too, because some of the continued research that's going to be happening is in cyber, because we can formally describe what's going to happen in physical impact. Cyber is a little behind. We're about maybe a year to 2 years behind in cyber. We can't formally describe cyber the way we can physical. You know this. And there's continued research on this with some of the folks that I flashed their pictures up earlier.
I didn't look at this as a sales pitch by any. No way would I
No, but I'm trying to be very careful about that.
I think there's something that you do bring up that's pretty valuable in that you're also demonstrating the entrepreneurial aspect of it. You don't really have a lot of
Right, because when we were talking about what we were going to do with the software, and there was like, you know, I have to be very careful about what I say now because this is being recorded. But, you know, we wanted it to be open source because we wanted to get it out there, and it makes a commercial pathway easier. Because anybody else can go out and jump and grab this software now, but we have a 3-year head start on you. And we know how to do this, and we've broken this thing 1,000 times before. The web front end is very stable. You build your own impact models. You can do this stuff now. And this is also a call for volunteers. This is a new open source project. Let's make this for the community. The engine is very nice. And I'd like to see people get involved.
So if I can ask a question about how you're cascading impact through the graph. First, are you maintaining 2 graphs, one for reachability, if you compromise this, you compromise this, and one for something like flowing, increases in power as you remove or add
yeah, that's like
assets, or is it a single graph structure?
No, it's multiple graphs. So you have the graph for the power, which is very formalized in many different commercial applications, planning software, whichever one you use. And we built an interface so that if you don't use PowerWorld, you use something else, you can write to the XML. And we can take in that impact data. And then on the other side, like for network, you need to just tell us, we need to see firewall rules, or in the format that the CSV sits in, so you can push the 2 things together. And I've completely forgotten your question at this point.
So,
the graphs. So, it's more than just graphs. But the online mode, for example, what we do is we can recalculate what this score is based on. Both the power grid's always changing. What's important on the power grid is going to change depending on what time of day it is. Because load moves all around. And then your corresponding, where's the hotspot is going to move on the cyber side too, because these are the things that are more important. And I don't think I answered the question.
No, it explains how you're flowing the cascading failures through to get impact by
because there's a
measuring
socket.
where power has exceeded threshold.
If you had PowerWorld, there's a socket that's open in the engine. It talks directly with PowerWorld. And then when there's changes, PowerWorld does transient stability analysis, and it also does a critical clearing time on the individual devices. And this is something that we literally just finished 2 weeks ago. So we can provide a critical clearing time in PowerWorld for individual relays.
Now, are the attack paths through the, are you modeling attack paths on the attacker side? As in, they got into this, and with this they can get into this, or are you more modeling just if they, we know that this is connected to something an attacker could potentially touch, and therefore if it goes down, we see this. And are you modeling failure modes other than just availability?
Yes. So it's a combination. We look at the firewall configuration, so we get a reduced set of network attack surface from that availability, and then through Nmap, if you have Nmap data, and we've done actual Nmap scanning, and we've artificially produced Nmap scanning to interrogate the US CERT database, so that these are the vulnerabilities that might be on this system. So if there is a vulnerability that matches the software that's in the system, it's going to percolate up on the list. And this is also something that can be calculated over a period of time or iteratively. Is that iteratively? Yes.
And then when you're prioritizing assets by likelihood and impact, are you just kind of using some kind of 5x5 matrix for impact versus likelihood? How are you weighing those 2 together to get your single, this is the most important? How do you combine those 2 orthogonal vectors in the tool?
There's a paper you can read. It's the answer is longer than I can get to right now, but it's also a research topic. We make some decisions about what formulas we use to come up with these indexes. We test them against the utilities that we're going out with in the real world, and we're getting close. And one of the things that I'm really happy to release the software out to the general public is we want to know how close we are and how we're calculating both performance index on the network side and then the impact, and then blending them together, because we started out first using game theory, and that was very NP
Yeah.
problematic, and then we went to depth first search. You know, we've got a lot of PhDs on this project. Lots of papers were written about this, but it all came down to practically, how do you reduce the attack surface so that it's big enough to calculate, but then it's still interesting? Because I
Yeah.
can reduce the attack surface down to 0, then we can calculate everything. It's easy. So you got to find, there's a middle ground in there somewhere, and then the more people that use this, we can find how far can we take today's electronics. Because I think we can get much further now than we could 20 years ago, but no work has really been done on modernizing this kind of planning.
Okay, thank you.
That's a good question. Thank you. So, anybody else? So, thanks. I think that maybe the electrical engineering part would have been a little longer if Kate had actually come. And appreciate everybody's attention, and just go out and get the software and tell us what we did wrong. Thank you.